Okay, so welcome everybody to lecture number 5. So a couple of administrative things to begin with. Who doesn't have a project and a team yet? Okay, now keep your arms up. Okay, look at each other. You should be talking to each other right after this class. Okay, good. You can put your arms down now, but basically remember who you are. So the thing is, in order to get started with projects, here's a deadline. 2/10/2014. By that deadline, you must have picked a team and a project. And what you need to do is send a one-page summary which has the following thing: a title, abstract, and who actually participates in the team. And you need to send it to 10.801.aopt@gmail.com. So by that time, you need to have sent this. There's no reason why you can't send it earlier than that deadline, right? So if you don't have a team yet, either join an existing team or, well, form a team. Couple of requirements for projects. So first of all, the team should be 2 to 4 people. So there are no exceptions to that. In particular, I'm not going to accept a nobody likes me, I want to do a project on my own. Or everybody else is too stupid and I want to do a project on my own. By the way, this has all happened in the past, so I'm not making this up here. Or we love each other so much and so all 5 of us want to do a project. No. That's also happened. Okay. Secondly, choose your team partners wisely, because otherwise sometimes you get the I really can't stand the people I signed up for in a team with. I want to do it on my own. It's not going to happen later. Good. So, okay, common sense. What you'll learn through that, and that's part of the reason, is later on when you have a real job, you will probably have to work in a team, be that in academia or be that in industry. You'll need to be able to get on with people. Otherwise, people will not want to work with you. Very obvious thing. So, it's good practice. The deadline there is mainly there to make sure you guys get started thinking about it and working on it. So a couple of things that you need to worry about. First of all, it's not okay that you take last semester's paper and submit it as project for this, right? So we will check Archive whether you've uploaded your paper in the past, and if you then submit that as a project now, that's not okay. I'm saying that explicitly because, again, that happened last semester with somebody. They fixed it in the end, but it wasn't much fun for everybody involved. Okay, so don't do it. It's perfectly reasonable if you pick something that's related to your academic research, right? So that might also govern a little bit on who you team up with. Remember, there's a team, so that means if you have 4 people with exactly identical abilities, that's maybe not the brightest idea. So it probably helps if you have somebody who's good with math and somebody who's good with a computer and somebody who's good with ideas and somebody who can write well. That makes a good team. Okay. If you have 4 people who are great at all 4 of those things, it's even better. But basically, you don't have to be a jack of all trades in order to be a really good team member. It's perfectly okay if you're very strong at one of those things. Just find somebody else who complements you. I mean, this is all common sense, but just make sure you do this well. Couple of things, given that this is an 801 course rather than a 701 course. So the project actually counts a lot. So you should be able to answer the following questions. Why are you doing this project? You should be able to answer this without a lot of hesitation. As in, why does somebody care? And also, what can you do if you accomplish what you set out to do? So do the following thing. Google a guy called Heilmeier. He has his own Wikipedia entry, George Heilmeier. And he has something called Heilmeier's criteria. It's a list of about 6 or 7 criteria, depending on how you count it. They're very common sense things that you should be able to answer about your project. If you can't answer them, you have a problem. Okay. And these are basic things like, well, can you explain it to an idiot? Or, well, why would I care if you actually do, you know, what you set out to do? And why was it not possible before? Okay. So really basic stuff. Good. So with that out of the way, apologies for Monday. I went 10 minutes over time and didn't realize it. Anyway, okay, won't happen this time. Now, before I get into today's content, are there any open questions about Monday's lecture? So I think some things were not super clear, or some people would have wanted some things to be explained in a bit more detail. May I ask a favor from you? If something is not clear, ask a question. Don't be embarrassed, don't be shy, because if something's not clear to you, it's probably not clear to some other people as well. It's very unlikely that you're the dumbest person in the room. Most likely, if something's not clear to you, other people are also not understanding it. So don't be shy. This is really useful for me. It helps me calibrate the class. Or Surit likewise. So you're helping not just yourself and all the other students, you're also helping me. So therefore, as a favor, please do so. If something's not clear, I mean, sure, I'll still be out there after class. You can also ask Ina or Yuxiang. But then it's kind of a Chinese whispers thing where you first ask Ina and then Ina tells me and then I explain in class and I'm probably explaining something very different from what you wanted to know. So do me the favor and ask. Good. So now let me ask you a question. Who knows what a hash function is? Okay, good. Most of you do. Let me just briefly explain what a hash function is, because today we'll be using hash functions and related things. So in the most basic setting, a hash function is something that maps from some domain into, well, let's say a set of integers, for instance, 1 up to n. Sometimes this can actually be R. If I have, for instance, one of the Indic and Motwani type of hash functions for LSH. But in this case, I'm just going to use a mapping into integers. Now, this thing is super useful, for instance, to replace a random number generator. And I can also use a random number generator to construct myself a hash function. So first of all, what I could do is I could have something of the following form: hash of 1, hash of 2, and keep on going. And this would generate integers, in this case, between 1 and n. And I could use this in lieu of using a random number generator. So rather than invoking rand, I can just do this. The benefit of using a hash function instead of a random number generator is that I can go back here and ask, well, what was the second value that my random number generator created? And I don't have to go and explicitly store this afterwards anymore. I can just look back at this. There's an obvious thing that you can do if I don't want to have random numbers between 1 and n, but for instance, just floating point numbers. Well, I can do something like hash of x divided by n. And this is going to give me, well, something that's between 0 and 1. Make sure you do the int to float conversion properly. Otherwise, you might get interesting things. So there's absolutely no point in implementing your own hash function. There's something called murmur hash, and you can actually download that for free from Google Code. SM hasher. And it's about as good as it gets. It's very fast. One of the fastest hashes that you can implement, and it's also very high quality. Now, the obvious question then is, what do I mean with high quality? So the first thing that you want is you want to have, that the probability of over the hash functions, that hash of x equals I is to be 1 over n. This is a very basic thing. So in other words, I want to make sure that the hash function uniformly maps, my domain into these numbers. That's something every self-respecting hash function should, satisfy. Okay? Yes?
Do you mean this for all x?
Yes. So for all x, the probability over the random choice of hash functions has to be uniform. So what I'm assuming is that I have some pool that generates hash functions. And I'm drawing a random hash function from that. And this is basically my only source of randomness.
The hash function itself is not random.
The hash function itself is random.
No, I meant, sorry. The function is random, but
yes.
It does not itself perform random
yes, exactly.
in order to give you...
Exactly. So what I do is I basically push the button once and out comes a new shiny hash function. Now this one will take all sorts of arguments, and each time I feed the same argument into it, it produces the same output. However, next time I push that button and get another hash function out of it, it might do something else. In practice, you don't necessarily do this very much unless I truly want to have different hash functions. Hint, if I have something like this, SM hasher, so this murmur hash, how can I create different hash functions out of it? Well, it's very easy. I just feed, if I wanted to have h sub I of x, so this is, some hash function, I could just simply define this to be hash of x concatenated with I. Right, so if these are strings, I just attach I to the string, and I'm done. These will now, for different i's, is going to give me different values. So whether I use the same hash function and attach I, or whether I have different hash functions, it's the same thing. It's a very simple practical trick. Mind you, in Python, this doesn't always quite hold that they are very independent then, because the Python hash function actually has the property that it tries to give you similar hash values for similar inputs, which has some benefits in some cases, but it can really foul up your algorithm if you're not careful. Okay. Any questions about that so far? So given that this is the most basic thing that you can ask for, you can ask for something a little bit more extravagant. Maybe something that probability over all the hash functions, hash of x equals I, and hash of x prime equals j. This needs to be what? What's that probability? It needs to be what number? Yeah, so what number has to be on the right-hand side? 1 over n squared, exactly. So this is what you call a pairwise independent hash function. A perfect hash function satisfies this not just for pairs or triples and so on, but it satisfies it for everything. By the way, this was sloppy. There's something missing. Which condition do I have to impose for this to make it non-stupid? Exactly. X must not be equal to x prime. Right? Very good. So this is, very basic requirements on hash functions. Whenever needed, I'm going to assume that I have an ideal hash function. This just simplifies our proofs a lot. In practice, there will be some cases where we'll go through cases where we have just pairwise and so on. This usually makes the proofs a lot more technical and harder to work through. And it's kind of a badge of honor if you can prove that your algorithm works for real hash functions with, more restrictive assumptions. But yeah, it also makes the proof really hard. So for instance, there's this wonderful paper about consistent hashing and random trees by David Karger. And probably the fact that it took a long time until people understood how cool the idea was is largely due to the fact that he actually worked it through for pairwise independent hash functions. And so the idea is straightforward. The analysis is non-trivial, to put it mildly. OK. But we're going to keep things simple because I just want to get concepts across. So the first thing that we can do with this is, for instance, we can get permutations. So, well, if you think about it, what a random permutation is actually an encryption, right? So if I have the following thing, I map x into crypt of x, then I want to be able to have a backwards mapping which maps the encryption back into x. Otherwise, well, you know, what's the entire point of an encryption? And if I have, let's say, you know, keys in the range 2 to the n here, and it maps into keys of the range 2 to the n, then I basically have, in doing so, defined a permutation of those keys. Right? So it's very easy. Now, you might think that actually coding up such an encryption is really hard, but it isn't. There's something called the Luby-Rakoff pseudo-random permutation generator. Pseudo-random permutation generator. And if you search for him on search for that on Wikipedia, you'll find a page that goes with it. And it actually uses a very, very simple construction. And since it's so simple, I thought it's probably worthwhile sharing, because occasionally you do need permutations. And there's a very awkward way of getting a random permutation by first generating random numbers and then sorting, and then basically, so this is how you would primitively do it in MATLAB. You basically sort, you keep the sorting index, and that's a random permutation, right? But this allows you to do this without actually having to instantiate the entire thing at once. And it uses the following iteration. Let's say I have a pair x and y. I map this into y and x XOR hash of y. Okay. I define this to be some function f of x and y. So this function f maps x and y into something where I move the y's to the left-hand side and I XOR x. Now, it turns out, and this is basically what these gentlemen prove, that if I do this 3 times in a row, so in other words, f concatenated with f concatenated with f, this will give me a cryptographically strong permutation. Okay. And there's a very nice proof that if you want to know that paper, I can give you pointers to that later. But this was quite an improvement. Now, to see that this mapping here is 1-to-1, it's very easy. The y's are just identity, so that's easy. The x's are mapped into x, and then it's XORed with something else. And so x XOR with something else is also the identity. So each of those pairs is 1-to-1. So therefore, we have a, bijection. If you repeat a bijection 3 times, it's still a bijection. And so therefore, you get exactly this encryption. And then the hard part is to prove that this is actually, an encryption. Okay. So this is sometimes useful if you want to get random permutations of sets. We're actually going to use random permutations of sets later on. Okay. Yep.
Is there some magic with 2, or is that just because it makes it cryptography?
Well, you need at least 3. For 2, so first of all, for 1, it's obvious that it can't be, right? Because you can still read off the y's. For 2, it's not strong enough yet. So I can point you to the paper where basically 3 is the key point. And yeah, it's, again, derived for, I think, ideal hash functions.
What's the property of being an encryption?
Well, the property of an encryption is that there is no there's no known polynomial time algorithm to revert this unless you have the keys, or unless in this case you can factor some large prime numbers, or whatever else drives this hash. So there's I can point you to the paper afterwards. There's a cleaner derivation rather than by Luby and Rakoff. It's actually very well written, but slightly tangential to the class. But yeah. So why do we do all of this? Well, what we're really after is what's called a locality-sensitive hash function. This will come back later on when we look at the random projections of Indyk and Motwani, but I'm actually going to show you something a little bit cooler right now. Okay, so it's a map from X into hash of X, and this is such that the similarity between arguments is approximately preserved. In other words, with high probability, we have that the distance between hash of X and hash of X prime divided by some other distance between X and X prime, that's the one that I want to hash, minus 1 is less equal than epsilon. I mean, there are other ways how to write this. For instance, you can just show that, this is both an upper and a lower bound within epsilon of that original distance. But for practical purposes, it just means if I have some distances before and I hash my object, then afterwards I get an object that allows me to compute distances very cheaply. And what we'll encounter a bit later is when we take, for instance, do the following mapping. Let's say X is a tall and skinny vector. Then we'll take some matrix M. Okay, this will be a bit longer. And this matrix M will have Gaussian entries with zero mean and variance that's suitably rescaled, but with all independent entries. And it will turn out that this is going to be a locality-sensitive hashing for X whenever we want to, for instance, reconstruct things in Euclidean space. So we will be looking at a paper by Piotr Indyk and Rajiv Motwani. And then there's a couple of very nice consequences out of this. But this is one construction that we will be touching upon quite a bit later. Also later, because it requires slightly more refined mathematical tools, instead what we'll be doing today is we'll reuse the construction that we talked about on Monday, and for that we only really need Chernoff bounds. Okay, so the example that we'll use today is this one here, where we have some vectors x and x prime, and I have some w, and I'm going to map x into the sign of w dot x. And so this gives me, for different values of w, different choice of w, that I'm drawing w from a normal distribution with zero mean and unit variance in d dimensions. This will give me, a bunch of random signs. I mean, I can clearly see that the probability of a particular sign being 1 or minus 1 is 1/2. And then the idea is that I can use this to measure somehow the similarity between x and x prime. So the thing that we already had from Monday was that the probability of, let's just call this thing here hash sub w of x. Probability over all w of hash sub w of x being not equal to hash sub w of x prime was going to be phi over pi. Because that's exactly the size of the angle in between. And the really cool thing about this is that this is independent of the dimensionality of where the x's lie and where w lies. So this is actually a very useful thing, because now, regardless of which data I started out with, I can obtain from that an estimator of the angles between x and x prime simply by mapping x into a set of those bit hashes and then just compare bits between them. So what you get is obviously through that in expectation over all the hash functions pi over 2m hash of x. So I'm now assuming that this is an m-dimensional vector, basically hash of w1 up to hash of wm. I define this to be hash of x to be this vector here. That hash of x minus hash of x prime. And these are 1s and minus 1s, so that's why I need the 2 here. This is nothing else but arc cos of x dot x prime. So why would you care about doing stuff like this? Well, it's actually quite straightforward, right? First of all, if I have this, I can reconstruct inner products directly. Let's do that. So I know that for general x, I have that the inner product between x and x prime is given by the expectation over w of, well, actually we could pull the norms out here, but it's the norm of x times the norm of x prime times, and then now we need to get the cosine, so we have cosine of, well, pi over 2m of hash of x minus hash of x prime. So in other words, in expectation, this is a well-behaved thing in terms of getting the norms. Actually, it's not quite true. I would actually have to, okay, sorry, this is, it's approximately that. Does somebody know what went wrong if I take the expectation here? Well, cosine and expectation do not commute. That's the problem. So in other words, if I have in expectation of a w arc, well, basically if I drop the cosine, then I get exactly this divided by norm of x and x prime arc cos, then the expectation is correct. So the correct theorem would be cos x dot x prime this equals the expectation of pi over 2m hash of x minus hash of x prime. That's it. Well, the price that you pay is not too huge. And we'll get to that in a moment. Okay. That's why this is just an approximation. Okay. So let's look a little bit at why somebody might actually want to do this. So, for instance, let's take documents. So documents might have maybe 1,000 words. So X is a document, 10 to the 3 words. Now, in order to take an inner product between a document and some other vector, let's say I want to classify whether something is spam or not, well, I need about maybe 1,000 flops. Right? That's basically looking up the number. And that's actually not even counting memory latency, because since it's a sparse vector, you know, you're actually going to have random memory lookups. So this is going to cost you something in the order of, each memory lookup is going to be in the order of maybe about 100 nanoseconds. So in other words, 10 to the minus 7 times 3. So this is going to cost you in the order of 10 to the minus 4 seconds. That doesn't sound like a lot, but if you have to compute that many times, it actually adds up very quickly. Okay. Now, on the other hand, if you use this hash and you compute that beforehand, let's say we take about 64-bit hashes. Then most modern microprocessors can do that in a single CPU core in one clock cycle. So the AVX or SSE instruction set, or even your cell phone, they all would be able to compute Hamming distances in one clock cycle for that size of vectors. So in other words, we're talking about one clock cycle to compute this Hamming distance, and then, you know, another 2 clock cycles for each of the multiplications. And then, you know, adding in, you know, the normalization and a few other things, we're talking something in the order of 10 to the minus 8 seconds at the very most. Probably better than that. So in other words, this is 4 orders of magnitude faster than doing the exact thing. That's why it matters. Even if you were to implement the Hamming distance computation explicitly with C code, which you absolutely should not do, you should link against the library, you'd still be about 2 orders of magnitude ahead. Yep?
You do it from the normal, right? So it's not a bit. It's not quantized. Do you quantize it somewhere in there?
Okay, good question. So hashing X is expensive. But then once I've hashed it, I just work with a hash most of the time, and there, yes, you quantize it, but you're taking the sign. So it's going to be 1 or minus 1 or 0, 1, 0, 1 respectively. So you're raising an extremely important point here. So converting the document itself into its hashed form is not cheap. As a matter of fact, in order to do this, I have to perform 64 of those operations, right? So this is going to cost me something in the order of 10 to the minus 2 up to 10 to the minus 3 seconds. Right? That's actually very expensive. 10 to the minus 3 because you might be able to do maybe 4 floating point operations in one clock cycle if you're using AVX instructions. So basically if you're using the vectorization in your CPU. But, you know, once you have this, everything is really cheap. It's also really cheap because the memory access is much cheaper, because now you're only pulling in a much smaller part of the memory. Because, you know, a single double, you know, just one double will cost you 64-bit. Of course, this is not exact, but this holds regardless of the dimensionality of the original data. Can somebody give me an example of where this would actually be quite horrible in terms of distinguishing observations? So where is being able to compute the inner product rapidly a lousy idea to distinguish things? Yep?
Stupid question. What exactly, so we have in the top right, h sub w of x is the sign of inner product
Yes.
of w of x. Our hash function is outputting a single bit.
In this case, so what I did is, with some very slight abuse of notation, I did this, right? I basically turned it into an m-bit long bit vector. So I parameterized the hash function by w, and then I said, okay, we're going to use, maybe 64 of them, and that's what we get. Yes. So, thanks. But can somebody tell me geometrically an example of where this can go badly wrong? So linear is kind of a good idea. So let's say this is the origin. And if all my data sits over here, then, yeah, those inner products are going to be really lousy. Okay? And since the guarantees that we're going to get are with regard to inner products, yeah, basically everything will pretty much hash into the same thing. So you may or may not get the pleasure of fixing this in your homework number 2. Namely, the question is, what can you do in order to make this problem go away? Or at least, what modification do you have to make such that afterwards you can still, compare those observations efficiently, even though they sit really far away from the origin. Exactly, you center it. Yes. You just did the homework for everybody. Yay! Okay, you'll get to work through the details in the homework, but thanks. It's good. Well done.
So what if it's sparse and high dimensional?
If it's sparse and high dimensional, then that doesn't really hurt you. I mean, they might still be very different. So all you have to be able to do is at some point, compute the inner product between w and x and compute the sign of it, right? So if x is sparse, well, fine. You pay a little bit more. The other thing that you might have to do is worry about how you get those entries w, because you might not really want to store all of them. This is actually going to be another homework. How can you avoid storing all those entries w if you don't want to? And basically, you can get away without storing even a single element of those. So.
It also seems to me that with a large amount of data, you might run into birthday, paradox-style problems.
Correct. Correct. So.
Guarantee is only for, right, it's up there, but if you have a million of these, you can
Exactly.
pretty often.
Exactly. So. Okay, so the question is basically, why is this a good idea? After all, if I have a lot of data, at some point, eventually something will go wrong, right? And, okay, we'll get to the birthday paradox in another class, but the point is, yes, it will go wrong. And if you throw away the data and just use the hashes and nothing else, then this is not a great idea. However, what you can often do is you use this and then combine it with some other checks and balances whenever you have a collision. You then go back and inspect your data. But the good thing is that at least then with a suitably constructed algorithm, and I'll give you an example of that at the end of the class, and where we actually use this for a exponential families model sampling algorithm, you can still get good performance, even though, individually things can go wrong. Yes?
This is kind of open-ended, but can you comment on the relationship between this and Johnson and Strauss?
Okay. So Johnson-Lindstrauss is this thing here. This is Johnson-Lindstrauss. So, in my opinion, the Simhash of Charikar is far superior to this. Here's why. For Johnson-Lynch-Strauss, so this is matrix vector multiply, you get a floating point number in each dimension. So therefore then, you are paying about 32 to 64 times more memory for essentially the same amount of randomness. We'll see that both things will go like order 1 over square root number of dimensions that you've picked. Secondly, this, well, basically requires you to have, so first of all, it requires more memory to begin with. It doesn't really give you much higher accuracies in terms of rates. And then afterwards, when you do comparisons, you still need to actually take inner products between those vectors. The one big benefit of using Johnson-Lynch-Strauss-like embeddings is that you can just happily throw that whatever algorithm that used a linear method in the beginning, and under certain circumstances, you can show that you don't lose too much. So you don't need to change your subsequent algorithms. But in most cases, this is not desirable. So because it, for instance, also compresses too much. So for machine learning, we'll look at something related, which is called a hash kernel. And we'll take care of that after we've looked at the count-min sketch, which is another sketching algorithm, which is also effectively can be thought of as a projection of the data. So Johnson-Lynch-Strauss and the locality-sensitive hashing a la Motwani and Indik simply was there earlier than this, probably about 5 years earlier. And this is why it gained a lot of attention until this came out. It has a number of nicer analytic properties because everything is nice, continuous, and so on. Or for instance, when you're dealing with matrices, you want to actually use something of that form. So there's a paper by Heilke Martinsen and Trop that we will go through eventually in this class, which basically uses this construction to design approximate low-rank representations of matrices for the purpose of solving efficient numerical linear algebra. So there's a lot more coming down the pipeline where we started here. But I just wanted to start with a much simpler algorithm to begin with. But thanks, this is very much to the point, this question. The other thing where this also relates to is, who knows about compressed sensing? Okay. So compressed sensing is basically one of those really ingenious ideas where you start with a sparse vector, you hit that with a dense or often dense, or at least somewhat interestingly behaved matrix. You get the dense object out of it that's much lower dimensional. And then it turns out that you can, even so you might even have some noise added, reconstruct the original sparse vector efficiently by, for instance, running a linear program. This is another example of where optimization meets randomization meets machine learning. And what people have very recently started to discover is that rather than storing those floating point numbers, it's sufficient to store just the signs of those inner products. And this goes under the moniker of one-bit compressed sensing. Okay, so, and at the moment people are sort of kind of rediscovering a couple of supervised classification results from machine learning, but now in the compressed sensing literature. And it's quite surprising, so when at some point I went to one of those talks and then I mentioned those results and they were like, really, does machine learning do this? And if you think about it, one bit is exactly binary classification, right? So they basically designed random classifiers on the data and use this to then reconstruct the sparsity pattern of the data. Okay, so this was a very, very long detour. Now, let's actually prove a couple of useful things about this. So we've already shown that in expectation, this is well behaved. Right? This just follows from construction because if it holds for one bit, then for m bit and averaging over them, it still has to hold. So this is easy. To prove concentration, we need something called a Chernoff bound. Who knows what a Chernoff bound is? Okay, most hands go up. Great. So I can be very brief. One version of it goes as follows. Suppose I have some random variables, xi, and they're in some range ai going to bi. Then I'm going to define some variable c to be sum over ai minus bi squared. And I then have the following theorem, that the probability that sum over I xi minus the expected value of those xi's, right, that this thing here is greater than epsilon, is less equal than e to the minus 2 epsilon squared over c squared. Bless you. So, in other words, with high probability, the deviation between the empirical average and its expectation is less than, is of the order of this quantity c here. Sorry, c squared. Okay, now let's plug in something slightly more useful, namely, suppose that the xi's are actually averages. So what you get is that basically, 1 over, if I make them 1 over m, right? So I get 1 over m here, I get 1 over m here, right? And then, of course, the epsilon scales accordingly. And so what we get is m epsilon squared over c squared, where c squared now is just, okay, get a minus b squared to make it correct. So if you solve this, so let's say delta is e to the minus m epsilon squared over a minus b squared. So we take the negative log, and so I get that m epsilon squared over a minus b squared is minus log delta. And then you can see that, for instance, the needed sample size goes like 1 over epsilon squared. In other words, if I need to double my accuracy, I need to have 4 times as many observations. That's the maybe not so terribly useful way of looking at it. The more useful one is if I write it in terms of epsilon, and you'll see that basically epsilon is, and we lost the 2 here, sorry, is basically minus log delta over m square root of that, and then here we have an a minus b. Right. So in other words, the length scale scales according to how large the random variables are. Well, that's kind of a no-brainer. It goes like 1 over square root number of observations that I'm picking, and it's logarithmic in the failure probability.
Isn't there Hofting?
Yeah, so Hofting is a special case of that. Now, there is, so this guarantee actually holds a little bit more strongly. There's a theorem by McDiarmid. I think 1995. And the difference is that here for Chernoff, we needed averages. We needed sums of independent random variables. I forgot to mention they have to be independent. What McDiarmid did is he proved the same inequality whenever I have functions of random variables. And what I then have to do is I have to check, well, if I change one of the arguments in the function, by how much will the function itself change? And obviously, an average where each of the arguments is bounded between a and b will change by a minus b, square goes here obviously, by a minus b. But for instance, if we wanted to get our hands directly on that expectation, right? You can see that cosine, well, now really mangles all those terms together. And if I change one of my hash function, one of the dimensions in h of x, this will change by at most pi over 2m. And so, in my entire concentration of measure inequality, I will get a pi over 2m term here. So this will basically be replaced by pi. And yeah, that's about that. Now, what this would do is it would help me prove that with high probability, the empirical average is close to the expected value for the cosine. So that's why I said this is not quite true. This is true, and for this is an approximation. But yeah, you can maybe work out the difference between the cosine of the expectation and expectation of the cosine. It's a little bit messy. Okay. So we got that far. So from that, we already see that if you don't need amazingly high accuracy, but just with reasonably high probability, a good measure of similarity between documents or other vectorial objects, you can get it. What you immediately also can see is that as you get more documents, right, you will want to do something with delta, because you want your failure probability to be low. But you can see that the number of dimensions that you need will only increase logarithmically with the amount of documents that you're going to process. And that's usually a very benign thing to do. Okay. Now, yes?
So I'm assuming that this discussion you were referring to, your aim was, how do I go from having the 64-bit hash to calculating the dot product if I need it?
Mm-hmm.
This
Yes.
is what you were describing.
Yes.
So, why don't you just use the true theorem? Why did you use this approximation where you can actually, when you have the second line that you wrote, you have the R cross
Correct.
number expectation. You can just take that average.
Yes.
And then take the cosine.
Exactly. That's basically what you do in practice anyway. But basically, this doesn't give me a guarantee on x dot x prime directly. And so what you actually need in some cases is, for instance, for an exponential family sampler, you actually need to be able to approximate inner products. So at some point, you'll have to invoke the cosine and do all the stuff. But for instance, if I just want to have document similarity for fast retrieval, I may not need this. You're absolutely right. So as a matter of fact, this is one thing that I'm going to show you now. So this is one of those really very simple but very nifty results. And that it's basically the first section of Charikar's paper. By the way, there will be links to references for various papers that I'm using in this up online. But for the moment, basically, there's a paper by Charikar from 2002. It has the very unassuming title along the lines of using randomness for approximate distance computation. And yeah, it's actually a very, very nice paper. And we are going through a very small subset of this today, and well, possibly in a week's time from now. We'll get back to this for some of the other constructions in that paper once we've, for instance, looked at the Motovani and Indyk constructions, because some of them use precursors in their, for their proofs, and then the proofs are only sketched, and it wouldn't do you much good to go through those proofs before actually having gone through the other papers. Okay. So what he does is he actually defines what he calls an LSH scheme and simply defines a similarity function between x and x prime. And it's just defined as the probability over hash, all the hashes drawn from some distribution of hash of x being equal to hash of x prime. So you can immediately see that the Simhash here satisfies this criterion because basically those different hash. So I'm switching back to hash functions, just outputting maybe a single bit. So before that we had entire vectors. So with some abuse of notation, we're now switching back to this case. Okay, so he just defines that as a similarity. Now, the first thing to notice is that this actually is a kernel. That's not in his paper, but it's a very simple thing to prove. In other words, what it satisfies is that the integral over any function f of x prime, sim of x and x prime, dx prime for any square integrable f is greater or equal than 0. So this follows directly from the fact that for any given hash function, the Dirac delta function, in other words, checking whether hash of x equals hash of x prime, is an inner product. Okay, well, that's just, basically think of, a discrete valued hash of x, which you need in this case anyway, otherwise it doesn't make much sense. So then you can write hash of x, you map it into a vector with all zeros, and exactly at the position hash of x, it has a 1, and the rest is all zeros, right? And so hash of x in a product with hash of x prime, which maps again into zeros, maybe here's a 1, and then we have zeros again, of course, is going to be 0 if these two positions don't match up, and it's 1 otherwise. So this is an inner product. Now taking expectations, in other words, therefore linear combinations of inner products, non-negative linear combinations, will preserve this fact that these are inner products. So this is a kernel. Okay. The other really nice thing is that the Simhash satisfies the triangle inequality. X dot x prime plus sim of x prime x2 prime is greater or equal than sim of x and x prime. Sorry, x2 prime. And again, you can immediately see that by picking a single hash function. And what you have there is you're basically comparing whether delta hash of x prime plus delta hash of x prime hash of x prime to prime sorry, I screwed up, namely 1 minus this plus 1 minus this 1 minus this, right? Because basically what I have to check is, whether the cost for, so basically if x and x prime are different, this is going to be 1. So, this can only really take on 2 different values here. Let's say this is 0, so this means that x and x2 prime are the same. if x and x2 prime are the same, then two things can happen. Either x prime equals x, or it's not the case. If it equals x, we have 0 throughout, so it's all satisfied. If it's not equal to x prime, then I get 2 greater or equal than 0, done. If, on the other hand, x and x2 prime are different from each other, then the only thing I could do is I could either match up x prime with x or with x2 prime, so done. So this shows that 1 minus Simhash satisfies the triangular inequality. Interestingly, another thing follows immediately from the fact that this is a Mercer kernel. It follows from this also that basically sim of x and x plus sim of x prime and x prime minus 2 sim of x and x prime square root satisfies the triangular inequality. Is actually a metric. Okay. The reason why this holds is because if it's a Mercer kernel, it's an inner product, and what I've written there is basically just the squared, the norm of the difference between, you know, x and x prime in that space. So you can see how you can get a number of fairly not so obvious looking results in a very straightforward way. Okay. So there's a useful reason why you might want to do this, and one of them is in the context of shingles. So this was something that was introduced by Andrei Broda. So he's the guy who shares the Kanellakis Prize with Charikar and Indik. It's also called a minhash. It's by around 1998. And he's written a series of papers on that. Basically, this entire thing arose from the fact that, so he was working at Alta Vista at the time. And, well, basically, you know, once upon a time before Google, there was a search engine called Alta Vista. And one of the problems that they very quickly ran into is when you crawled pages, you might end up with duplicates. And duplicates are really, really bad, because if you return duplicate search results, well, users will not like it. So users are very, very sensitive to identifying if something is duplicate. Secondly, it slows down your entire computation, so you don't like it for that reason either. Now, if you crawl the web, you want to very quickly identify all the duplicates, but this is expensive, because comparing all pairs of documents is a quadratic operation, so you can forget about that. So instead, what he came up with is what's called shingles, and I'm going to show you how this works. So the first thing that I'm going to show you is what's something that's called a Jacquard coefficient. I'm probably butchering the spelling here. And it's defined between two sets. So the distance between set S and set S prime is defined as the size of the intersection divided by the size of the union. So to draw the Venn diagrams, S, S prime, S intersect with S prime. It's basically the size of the overlap relative to the total size. And what I'm going to show you is that this actually is an example of a locality-sensitive hashing scheme. And it satisfies all those conditions up here. So in other words, it's a kernel, it satisfies the triangle inequality, and this is also something that will, it's a metric actually. So, how do you do that? Well, it's actually very easy. In hindsight. So I'm going to map S, this is a set, remember. I'm going to map this into a permutation of that set. As a matter of fact, I'm going to permute all possible elements in my domain. And so what I'm going to do is I'm going to apply this permutation to that set. So this assigns each of the elements a number. I'm going to take the min of this, and then I'm going to invert the permutation. In other words, I'm going to find out which the element was. So if I have a bunch of elements, I'm going to pick this guy here out of my set S. And this might be, the word dog, house, is, and so on and so on. Right. Now I do this for S, and I do this, so basically, let's say this is here. So I'm mapping S into a single token from that, and that token is called here. I'm going to do the same thing for the set S prime. And if the word here is in the set and it's also the smallest one, then I end up picking it, but maybe I get this, and this has a value of -1. It's called new, and I have some other guys here, whatever. And then I'm going to check, so, whether the two smallest elements match. If they match, I count it as a 1, otherwise I don't count it. So it's a very, very simple idea. The way how you would implement it is you would take the hash of each of those words and pick the word with the smallest hash value. So that's why it's called a min hash. Okay? Now, what you can immediately see is that for the purpose of finding out what the expected value of this agreement is, I can ignore all the elements that occur neither in S or in S prime. So now I only need to look at this, and I need to consider what are the chances that both the min hash of S and the min hash of S prime will have the same argument, will have the same value. Well, it's actually very easy, because it happens exactly when the smallest element from the union is in the intersection. Let's say it's this element here. Now, what are the chances that this happens? Well, the probability is exactly probability of the intersection divided by the total size of the domain. So what I've just shown is that, okay, let's call this thing here hash of S. The probability over all hash functions that hash of S equals hash of S prime equals the Jaccard measure. Okay. Now I can do that for different permutations, and I see immediately that this satisfies exactly these conditions up here. So what I've therefore shown is that 1 minus this satisfies the triangle inequality, which is super tedious to prove directly, but very easy to prove by going through these results, as in confirmed by the authors. And yeah, you have a simple hashing scheme. Now, the obvious question then is, well, I mean, this is this is kind of useful, but it's a little bit awkward because if I want to extract several hashes of this, I need to permute things over and over and over again. And so what was then suggested as an approximation is not just to take the smallest, but the k-smallest terms. So I basically do the following thing. I permute S. I take the k-smallest, and I invert the permutation. This is very easy to do. I compute the hash of each of the entries and just map forwards and backwards. This is not quite correct anymore, but it's good enough for all practical purposes to identify duplicates. There is a better way, and that's unfortunately computationally a little bit more expensive. So Ping Li has been working on this quite a bit. And he calls it conditional random sampling. And with that, he fixes some of these problems, albeit with an algorithm that is, let's just say, computationally rather much more costly. So the key idea of what he's exploiting is that rather than just storing, what the smallest values are, I can also keep track of the hash IDs. Now, what the hash IDs tell me is how many elements I had in the set to begin with. By storing this extra information, I can actually do a much better job at estimating this. And he's written about half a dozen, maybe a dozen papers by now on this, so have a look at his webpage, and he goes through it in a fair amount of detail. So this fixes a mathematical issue. In practice, for implementation purposes, it's a little bit less of a burning problem. So I'm going to conclude with how they actually then implemented this on Alta Vista to remove duplicates, and we'll look at more properties of the Simhash and so on in a week from now. Because Subrit will be teaching again next week. So basically imagine you have many billions of web pages. And you want to find out how similar they are. So the first thing that you do is you go in and shingle them. And so what you do is you basically take adjacent strings of words, let's say 4 grams or whatever. You compute their hash, and then you perform this operation. Okay. And so then you emit for each shingle shingle I of document S and also the document ID. You emit those pairs. You do that for all documents, and you can easily do that, for instance, in Hadoop. Okay. Then you join this and sort by shingle ID. So documents that are duplicates or near duplicates are going to agree on those shingles. You might get some false positives, and you can check on them later, but chances are there aren't that many duplicates overall. You just want to find the ones that are duplicates fairly quickly. Okay. So you sort. And you basically now get shingle ID of S. And then you get a long list of document IDs. S1. And obviously, just having a match on a single shingle isn't really a big deal yet. But if you have a lot of matches, you can assume that something is colliding. So basically, therefore, if the same document ID pairs occur in a lot of contexts here, we know that we're in trouble. So you therefore then, in the next step, you emit all the document ID pairs for the same shingle. You sort, and then in the end you just aggregate the clusters. So, can somebody tell me where this can go horribly wrong? And they actually had such cases where it went horribly wrong. Exactly. Exactly. That's the Achilles heel. If this list is long, I'm screwed. Now, this list can get long if I pick some word combination that's very common. What's worse is if I actually have documents that are repeated many times. Because now that list of pairs will scale quadratically with those documents. So it actually turned out that there were like 3-4 documents that occurred a lot. My guess is, for instance, stuff like the GPL text, right? Or some other text that everybody would just put on their web page for God knows whatever reason. So those broke it. And then there are basically very quick ways for first making sure that you get rid of those obvious duplicates. So for instance, one thing that you can do is you just hash those shingles as footprints directly. You look for things that are obviously identical to throw them out right away, and then you work separately for the approximate matches. So tricks like this will let you very quickly get rid of the really, really obvious identical parts, and then afterwards you don't have to pay quite such a price. So I think I need to stop here. We'll continue in a week from now. Any questions? By the way, this was good today that you guys asked questions. This was really, really helpful. Thank you for that.